Right. Hello, everyone, and good morning. My name is Dmitri Goloubentsev. I've been a quant for many years, working as interest rates on the interest rate derivative and XVA, etc. So I'm very familiar with all the quant problems you guys are facing. In 3 years, 3 year ago, I left my bank and decided to form my own company to work on a brilliant tool. I think that every quant needs, a good tool to execute AAD easily. Anyway, so this talk is going to be about our benchmark we did for American Monte Carlo, and applying AAD to American Monte Carlo efficiently is considered to be a very complex problem, and we decided to tackle that to demonstrate how it can be achieved. So what is AAD in real quant life? Difficult to integrate. You can hear that some projects are going on for years to get it done, and still no result. It's slow. Yeah, you need to integrate your active type throughout your code base, and this reduces the performance. Requires a lot of memory. Yeah, you need to be clever about that. You do hear a lot about checkpointing or other ways to reduce that, but generally it's the demands for memory are fairly high, and this is what sometimes prevents to execute it efficiently on GPU. Pollutes code with templates. That's my favorite. So people tend to go templates in C++ code base for performance reasons and for flexibility, but this slows down the development. It makes your code look very complex, and compilation time may be ridiculous. Hard to handle market data. Yeah, so this handling implicit functions is also not a trivial problem. Like AAD in principle works easily, but when you're faced with practicalities of quantitative work, you need to handle this, and this is also not easy sometimes. It's very hard to implement for callable products. And the reason for this is because normal Monte Carlo or simple Monte Carlo models, auto-callables, etc., they can be implemented using pathwise Monte Carlo, right? Where you don't need to hold all Monte Carlo samples in memory all together, but you can simulate path by path and just average prices and adjoints to get your sensitivities. But it doesn't have to be this way. I mean, it doesn't have to be this difficult, and there is a way to do and achieve AAD easily in your life. And we've done some work to address these concerns in the past. We've done some work to demonstrate how it can be easily integrated, how templates are not required and memory requirements are not that high, and how implicit function problems can be also handled fairly easily. But today, I want to focus on callable products. So the plan for today, we're going to look quickly at Longstaff Schwartz method. I'm sure everyone knows what it is, so it's going to be a very quick introduction. Right, so regression, to differentiate it or not. There are like lots of articles out there, and I have some references in the paper that goes with the slides. I recommend for people to review that. We're going to discuss intuition, like why you may want to differentiate regression and why it's not required sometimes. Of course, like when you want to execute AAD for callable product, you need to start with smoothing out all your discontinuities and payoffs and more. We will talk about that. LSM topsy-turvy. So how do you actually enable a adjoint path for LSM method? And what do you do for achieve efficient memory use and parallelization? So what do I mean by that? If you apply AAD tools directly to huge Monte Carlo with lots of vectors, regressions, etc., you quickly run out of memory and your performance will suffer. At the same time, Monte Carlo is generally very well suited for parallelization, but how do you achieve that when you need to handle regression that is introduces cross-path dependency. We're going to see some results and some performance results. Right, so quick LSM definition. I have a short PDF describing some maths behind it. So if you it will be handy if you open it from the forum page and have it in front of you if you want to know more details. But the whole thing can be split in 3 basic steps. So step number 1. In the first step, what we do, we simulate Monte Carlo and compute and store accumulated cash flows, exercise amounts, and values for the basis functions. So this data is needed to execute Longstaff Schwartz regressions, and this data is in vector form, right? So we do need to have it available in memory. But every time we simulate Monte Carlo, it can be done path by path. And what I mean by this are all the state variables that lead to basis functions, values, and accumulated cash flows of a particular trade. These values can remain scalar, and only the output of this Monte Carlo needs to be recorded in a vector format, in vector form. Right. So how does it look? Something like this. You start with market trades. You run through your normal model calibrations, etc., and you arrive to Monte Carlo to evolve your state variables and calculate fixing rates and calculate all the cash flows appropriate for the instrument, given the various outcomes of the exercise decision we need to make. So it could be exercise values if you decided to call, or if you don't call, you want to know what the accumulated cash flows are between exercise dates. So step number 2, you actually execute Longstaff Schwartz method. You run this regression backwards, and feel free to look up on all the details in the attached PDF file. But generally what happens, you take this vector data, you roll back from expiry to T0, and the result of this is regression weights coefficients. Note that this regression weight coefficients it's no longer vector data, it's a scalar data. So once this step is accomplished, we don't need Monte Carlo number 1, this line around. You can actually deallocate all the memory, and you can remove it, right? So the step number 3, it's a second Monte Carlo. So you want to produce a lower bound price, and to do that, you take regression weights and you use regression weights to determine your exercise strategy. And how do you do that? It basically gives you optimal exercise strategy if you believe it's optimal, right? If you believe your regression actually worked perfectly. But in ideal world, the regression coefficients will tell you exactly where to call and where to stop. And when your exercise strategy is optimal, your hold values expected value of the hold values should be equal to exercise value. Right, so regression, do we want to differentiate it or not? There are lots of papers around this subject, and I'm going to give a quick intuition why I think you may not want to differentiate it. So at exercise boundary, if it is optimal, your holding value is equal to exercise value. So if you change the market data and your exercise boundary moves, its move will not make a difference on the price because hold value and exercise value are equal. And if this is the case, you don't actually need to differentiate your regression. Well, you need to keep in mind that if you use a regression for something like XVA, so you use regression weights and Longstaff Schwartz basis functions as proxies for your prices of your instrument, future prices of your instrument. In this case, you do need to differentiate regression. Today, we're going to focus only on pricing, but the whole process can be easily extended to XVA and regression differentiation. So, like I said, we need to do some housekeeping for applying adjoint differentiation. So we need to smooth out all the discontinuities in our pathwise MonteCarlo. So this includes any discontinuities in payoffs. This is normal, like all digital payoffs needs to be changed to a fairly smooth function at the strike. And what also we need to do, we need to smooth out exercise decision. And this is the reason for that is because if your exercise strategy given to you by regression is not perfect, meaning hold value is actually not equal to exercise value, you do have a discontinuity there transitioning from hold to exercise back and forth. And this needs to be smoothed. And how do we achieve that? We achieve this by introducing option to partially exercise. So if in normal pricing mode, you go along the path and you make a binary decision on exercise or not, with this partial exercise, you allow to have a little portfolio of your trades, right? So you say my trade is of 100% when you start, but then at first exercise point you may choose to exercise 60%, and you end up with 60% exercise value and 40% of options that continues to run. And when you come to the second exercise, that 40% can also be split proportionally. So what it gives us a way to propagate adjoints to regression weights, and here you can see them as beta k. And without that, if you use a binary exercise decision, you simply cannot allocate any adjoints to your exercise strategy and hence to your regression. Again, if you look at XVA world, it might not be necessary because in XVA you use these beta coefficients directly, so you can easily allocate adjoints there. So how do you apply, like on top to bottom, how do you apply AAD to LSM? It might look something like this. So we did Monte Carlo 1. We computed all the vector data for cash flows and basis functions. We did run Longstaff Schwartz regressions and obtained all regression weights as a scalar. We now can execute second Monte Carlo and obtain PV. So for the second Monte Carlo, this second Monte Carlo can be executed pathwise, meaning we no longer need any regression data. So we can basically run it as normal, giving W's. And we can execute adjoint of each Monte Carlo path and propagate adjoints from PV to market rates. What we also can do is to propagate adjoints to regression weights, as previously described, right? So because our strategy is now smooth, we're able to accumulate all adjoints to regression weights. And the next step, what we should do is run adjoint equivalent of Longstaff Schwartz method. Now, this can be done manually. You can spend a week implementing that and making sure everything is correct and get it done. Or you can use automatic adjoint differentiation, but in vector format. Like its choice is yours, basically. But note that this is basically done once, and it's because the method itself doesn't really depend on the type of model you choose, on the type of instruments you're dealing with. It's fairly generic and can be applied to handle many model types and trade types. So what it allows us to do, it allows us to propagate adjoints for regression weights back to vector data for cash flows, basis functions, and exercise cash flows. And what remains to do is to propagate adjoints through Monte Carlo simulation 1. And how do we do that? We do it pathwise. We use initialization for adjoints obtained from this Longstaff Schwartz adjoint path, and we propagate that to market rates, and we do get correction for derivatives with respect to market rates that arises due to Longstaff Schwartz regression. So how it looks in details. Let's say we're dealing with step number 3, which is pricing, and this step easily can be converted to pathwise AAD. So instead of just going and running simulation path by path to obtain PV, you also execute adjoint differentiation for each path and calculate adjoints for market rates. Now, if you trust your regression, you can actually stop here. But if you want to differentiate it for some reason, XVA or not, or if you're in doubt that your regression performs well, go to step 4. Right. In step 4, we want to execute adjoint of step 2. So we need to propagate regression weight adjoints through LS regression. And the inputs for this step adjoints themselves for regression weights. And also it's Monte Carlo 1 vector values. Now, I did say you can throw them away, but you can actually keep them around for this step. It doesn't really like reduces overall memory consumption. It just makes use of these values at a later stage. So these values need to live in memory for a little longer. And output of this step, vector adjoint for cash flows, exercise value, and basis functions. Now, this is important. So we converted scalar adjoints for LS regression into vector adjoints for cash flows and exercise values. This is a somewhat bigger data set. And this is basically why you need to double your memory requirement. So the original method only needed vector values, but vector values from Monte Carlo 1. We now need also adjoints for these values. And we come to step number 5, and it's adjoint to step 1. So we need to propagate adjoints from Monte Carlo 1, and inputs to these steps. To this step is vector adjoints computed previously, and output of this step is the additional increments to adjoints to market and model parameters that arise because of the Longstaff Schwartz regression. But wait, you can ask, like, where is the tape data? Because if you want to propagate adjoints through Monte Carlo 1, it's not sufficient to have adjoints for the cash flows. You do need to know what happens for each path. How do you translate this adjoint to market rates? So keeping all Monte Carlo 1 path can be expensive, right? Because we're not only keeping all the state variables, we also need to keep all the local gradients for like basically tape data for us to traverse to. So it's expensive. It's not something we want to do. So what we can do instead, we simply can re-simulate Monte Carlo 1 using the same seed for random number generator, essentially recovering all tape data needed to propagate adjoints path by path. So in this case, we executed pathwise, so the memory requirement is still fairly small. You just need to keep your tape for one Monte Carlo path. You don't need to keep your tape for all passes at the same time. So how do you make it run efficiently? And what are the total memory requirements, and what are the opportunities for parallelization? So you can see that running steps 1 to 3 in just blindly applying scalar AAD or vector AAD, it could be very inefficient, right? You don't want your tape to go through all Monte Carlo passes. That's impossible for this. Implementing a vector AAD is also can be challenging. You may find yourself quickly running out of memory, and the whole thing may run slowly. So the idea is to exploit opportunities where you can execute pathwise AAD and use only native vectorization, native CPU vectorization. Here we talk about AVX2 and AVX512 vectors. It basically allows you to simulate your Monte Carlo in small chunks. So in one path, you can calculate 4 at the same time with no additional time requirements. So, like discussed before, Monte Carlo 1, it can be executed path by path using multi-threading and AVX as normal, and only minimal memory increase due to AAD. Step 2, it basically executed as normal, but as when we compute adjoint of LS regression, we also need adjoints for all the vector data, and this yields twofold memory increase for this step. And Monte Carlo 3, it can be executed pathwise AD as normal with minimal memory requirement, because you only keep your path AD tape data path by path, right? So you never keep it for all passes at the same time. So some results. Again, we just played around with this idea, and we wanted to demonstrate how well or how badly it performs. So we wanted to look at a product where Longstaff Schwartz may struggle to find the optimal exercise boundary. So we looked at the equity effects daily range callable node. This product, as you can see, so here this plot is basically on x-axis. We have spot value for the stock, and on y it's the price. So we basically go from out of the money, in the money, and out of the money. And on this plot we demonstrate binary price, the hard price, so a price with a yes and no exercise decision, and this should yield a higher price because it's more optimal, and the smooth price, so something where we introduce the partial exercise decision. You can see they are fairly close. Again, you can play around with the smoothing parameter to adjust how much value you're willing to lose, but gain nice continuity. So how actually since AAD sensitivities look like? Here you can see fixed AAD. So fixed AAD is AAD applied to the second Monte Carlo only. So we did not go through regression. Also, FD gives us bump and revalue risk, and full AAD is the AAD where we also take into account Monte Carlo 1 and Longstaff Schwartz regression. And you can see finally bump and revalue. It's fairly noisy, and I must say, like here, these plots we've built them using something like 500,000 Monte Carlo simulations for Monte Carlo 2, and I think it's 150K for Monte Carlo 1, and still bump and revalue it just goes up and down time to time, right? So you can see it's unstable. Fixed AAD is much better, much better improvement in terms of stability of the risk, but it's off, right? And you can see that the full AAD goes like an average of fine difference. So it's much better to bump in real value, which is you probably want when you bump your input data, you want your full AAD to reflect that. Right. So previous results was sensitivity to spot level accuracy. Here we're looking at a bucketed rate delta. So we're looking at the second rate on the curve. And you can see that the difference is somewhat higher. So probably Longstaff Schwartz regression takes into account behavior of stock itself better than what's happening with the rate curve. So maybe it's not I don't know, paying attention enough there. But you can see the difference could be substantial, and it's different in different areas, right? So if you go out of the money, you see no difference, but when you see some optionality kick in, you can see the difference between taking regression into account and not taking regression into account is substantial. And as expected, the bump in real value is very noisy, but full AAD is much better. Right, something similar for the volatility. Right, and in terms of performance, these tests were done on like fairly beefy, but not the latest and greatest Intel CPU. This particular trait, we did not try to optimize and play some quantity tricks that you probably want to do in practice. So we simply simulated 3,600 fixing time steps, and here we have annual call dates. And you can see how well this implementation can scale and compute AAD risks. So for 500,000 scenarios, if your native double implementation, meaning just sequential execution with no parallelization and using native doubled or no AVX vectorization, takes about 130 seconds. And if you still use only one CPU core and you apply vectorization plus AAD, you get it done in 77 seconds. So meaning you get price and all sensitivities quicker than the original double code. And the parallelization opportunities that we were able to exploit, namely parallelization for MonteCarlo 1 and MonteCarlo 2, allows us to scale better to higher CPU cores. And you can see the scaling is pretty good. We did not implement multi-threading for regression. It's also can be done, but you can see the regression itself isn't consuming much time. Right. Any questions? I hope. Basically, at MatLogica, we are not focusing on developing models. We like them to use them to demonstrate capabilities of AAD. We're basically focusing on developing a tool called AADC, and this tool is well suited to accomplish various quant tasks, but it's up to you to do the modeling. And if you're interested to see the source code for the benchmark and documentation, it's available on request. You can email me and we will get you going. Thank you. Right, so it's something we need to investigate. Like I said, we don't want to solve your problem, quantity problems. We're solving the technical problem, and I wanted to demonstrate how we can propagate adjoints through regression. We're happy to do this test for you. It should be very good. In our past experiences working with modeling interest rate swaps for XVA. I don't know, it's not exactly the same, but also requires a lot of simulations and large swap portfolio pricing. The performance we obtained was very impressive. It's on ballpark of you should get from GPU, but sometimes don't. But yeah. Anyway, if you get in touch with me, and we can try something for interest rate swaps. It should be much better. I mean, in terms of absolute performance time, what we were looking at with this daily range trade, it's actually daily simulation time. So it's a very big Monte Carlo simulations. We're talking about 3,600 time steps and 500,000 Monte Carlo passes. And mind you, to execute adjoint of this, Monte Carlo 1 was executed basically 2 times. Okay.
Thank you. Is there any more questions for Dmitri?